Today, we're diving into a fascinating paper that tackles one of the biggest challenges in AI right now. See, as we build bigger and more powerful models, they can actually risk collapsing into total chaos during training. This is the story of how a team of researchers found a really elegant way to tame that chaos. So, this is really the multi-billion-dollar question, isn't it? We're all pushing for more and more capable AI, but we keep hitting this fundamental wall. The very process of making these models bigger and more complex can make them incredibly unstable. The whole training process can just, well, it can just fail. So, how do we get around that? Well, to understand the solution, we've got to look under the hood. We need to start with a core piece of AI architecture that's been around for almost a decade now. You can think of it as the AI's information highway. Understanding this is absolutely key. Okay, so this is the standard residual connection, and its genius is really in its simplicity. It basically creates a direct bypass, an express lane for information to travel through all the different layers of the network. This is something called identity mapping. It just means the main signal gets through clean and unchanged, which stops it from getting lost or distorted. And that is crucial for keeping the whole training process stable. All right, so if that's the standard highway, what happens when we try to upgrade it? Well, a recent pretty ambitious idea tried to do just that, and the results were interesting, but also really problematic. Say hello to hyper-connections, or HC. The idea here was to blow out that information highway from a single express lane into a massive, multi-lane superhighway. Instead of just one simple path, it creates multiple paths that can actually learn and mix information as it flows. And in theory, that should make the model a whole lot smarter. And this right here is the crucial trade-off. The original design is simple and super stable. Hyperconnections are way more powerful, but by making all those pathways learnable and complex, they lose that vital identity mapping property. They basically trade that simple, stable express lane for a complex, totally unregulated superhighway. So, what happens when you build a superhighway with no speed limits, no traffic cops, and lanes that can just change whenever they want? Yeah, you get a massive chaotic pileup. The researchers themselves put it perfectly. Without those guardrails that identity mapping provided, hyperconnections lead to what they call unbounded signal amplification. Basically, the information flowing through the network doesn't just move along smoothly. It can explode to massive levels or just vanish completely. And this graph shows you exactly what that chaos looks like. This is visualizing the signal's strength as it moves through the model. You see those insane spikes? That's the signal just amplifying to extreme, totally unstable levels. It throws the entire learning process completely off the rails. Just how extreme are we talking? Well, at its worst, the signal amplification can reach, get this, 3,000 times its original strength. This is exactly what causes the training to get erratic and, in a lot of cases, to just fail altogether. Okay, so here's where the breakthrough really happens. The researchers found this incredibly elegant way to keep all the power of that multi-lane superhighway, but they introduced a clever set of traffic rules based on a really neat mathematical principle. Meet our hero, Manifold-Constrained Hyper-Connections, or mHC. Now, it looks pretty similar to that chaotic HC model from before, but there's one critical, invisible difference: a mathematical constraint that finally tames the flow of information. And that constraint is based on something called a doubly stochastic matrix. Now, don't worry about the name. You can just think of it as the perfect traffic management system. It makes sure that when information gets mixed between all those lanes on the highway, the total amount of information is conserved. It can be shuffled around, but it can't be uncontrollably amplified or lost. And wow, this just illustrates the result perfectly. On the left, you've got that chaotic signal explosion from the original hyperconnections. And on the right, with that mHC constraint applied, the signal is perfectly controlled. It's stable, it's bounded, the chaos is completely gone. It's night and day. So the theory is beautiful, the graphs look amazing, but does this new stable architecture actually perform any better? Let's take a look at the results. This graph shows us the training progress. The goal here is to get the training loss, which is just the model's error rate, to go down as smoothly as possible. You can see the old HGO model in green. It has that little bump of instability where it struggles to learn. But our new mHC model, in blue, it's a perfectly stable, consistent path straight down. Stability really does lead to better learning. And that better learning translates directly to better performance. Across multiple different tests, mHC, that's the final column, doesn't just fix the stability problem of HSC, it consistently outperforms it. And look, it does especially well on those really complex reasoning tasks. And here's the real kicker. This solution scales. As the models get massively larger, we're talking from 3 billion all the way up to 27 billion parameters, the performance advantage of mHC holds strong. This proves it's not just some little trick for small models. It is a robust, solid foundation for building the next generation of giant AI. And what's the best part? Thanks to some really clever system optimizations, all of these gains in stability, performance, and scalability, they come at the cost of only about 6.7% extra training time. That's a remarkably efficient solution. An incredible bargain, really. So let's zoom out. What does all of this mean for the future of AI? Well, it really boils down to a few key things. So we've seen this great promise, right? Wider information highways can make AI smarter. But we also saw the problem. Without any rules, they just create total training chaos. The solution, mHC, uses that elegant mathematical constraint to bring back order. And the final result? It's a practical, efficient, and scalable path toward building the next generation of powerful and, importantly, reliable AI. You know, what this breakthrough really does is remove a fundamental roadblock that was holding back our ability to scale AI. And now that we have a much more stable foundation to build upon, it leaves us with a really fascinating question. What are the true upper limits of artificial intelligence now?